Welcome back to part 2 of our Unit 4 guided notes on skills 10 and 11. Just a quick review from yesterday, the key concepts. First key concept is that when you raise a number to a fractional exponent, a rational exponent, the denominator is the index. So 1 over n power means nth root. The second key concept is when you raise something to a rational exponent, a fraction exponent, where the numerator isn't 1, then the numerator is the same as the exponent. It's whatever you raise the base to. It's how many times you multiply that base to itself. So the denominator is the root or the index, and the numerator is the power or the exponent. So let's jump down to question type number 3 when we are being asked to kind of go from a radical expression into something using a rational exponent. So here I can see that my exponent is 7 and my index is 3. So according to key concept number 2, I would rewrite this as x to the power of 7/3. The power is the numerator and the index is the denominator. Now for 9, we have different bases, right? So we need to think about what each of their different powers are. So for the base of 3, it's a power of 1. For x, it has a power of 4, and y has a power of 7. And then there is no index, which implies it's a square root or an index of 2. And then for each base, we write a different rational exponent for each one. So for the base of 3, it would have a 1 in the numerator and a 2 in the denominator. For x, it would have a 4 in the numerator and a 2 in the denominator. And for the base of y, it would have a 7 in the numerator and a 2 in the denominator. So I can see that the x simplifies. And if you remember, when we simplified radicals before, we would always do that. We would take the power that was under the radical and divide it by the index. And that's because of this rational exponent fact, that the number in the numerator of a rational exponent is the power under the radical. And that's why those can divide, because the index is the denominator of the radical. And we know that when you have something in the numerator over something in a denominator, those two things are dividing. So we can simplify this down to 3 to the power of 1/2 x squared, right? 4 divided by 2 is 2, and then y to the power of 7/2. So that would be our answer for number 9. For question type number 4, we're going to be able to take these radical expressions from before. These were radical expressions from before that we weren't able to simplify because of the fact that we hadn't learned about rational exponents yet. But now that we know about rational exponents, we can take these seemingly already simplified radical expressions and simplify them even further. So take this, for example. A 6th root of 36. That means I have to figure out what number times itself 6 times 1, 2, 3, 4, 5, 6 equals 36, right? A 6th root. That's what you're doing. You're trying to figure out what's that 1 out of 6 numbers that multiply to 36. And there is no whole number that multiplies to itself 6 times equal 36. So we would have just left it this way. But we do know that 36 is 6 squared, right? 6 times 6. So what we could do is we could say, well, this is the same thing as the 6th root of 6 squared. And then if we use key concept number 2, we could say, well, that's the same thing as 6 to the power of 2 over the index of 6. Right? The power goes into the numerator and the index is the denominator. And then we can reduce that fraction. We can say, well, that's 6 to the power of 1/3. And so that's equal to the cube root of 6, which, by the way, is that number that you multiplied to itself 6 times to give you 36. That number would have to be the cube root of 6. So we were able to simplify this radical. The cube root of 6 is simpler than the 6th root of 36. They're the same value, by the way, if you plug them in a calculator, but this is just simpler to look at. And we were able to get there through this bridge of rational exponents. It serves as sort of a bridge sometimes. Now over here with number 11, this was another problem this was another problem that earlier when we were learning about multiplying radical expressions, we would have looked at this and said, well, the indexes don't match, therefore you can't multiply these together. And at that time, that would have been, the case because we hadn't taught you yet about rational exponents. But now that I can sort of convert these into rational exponents, I can combine them because you can convert these to have the same base. Let me show you what I mean. So 8, let me do this over here. So 8 is equal to 4 times 2, which then breaks into 2 and 2. And so basically 8 is a combination of 3 factors of 2. It's 2 cubed, basically. Meanwhile, 32 is, you can kind of break that into, well, I guess 8 and 4, and then we know that 8 is 3 factors of 2, and then we know that 4 is 2 more factors of 2. So 32 is the 5th power of 2. So I can't combine them because the index matches, but I can now think of them as all having bases of 2. So this could be the 4th root of 2 cubed times the 3rd root of 2 to the 5th. And then I could convert them into rational exponents using key concept number 2. And so I could think of that as 2 to the power of 3 over the index of 4 times 2 to the power of 5 over the index of 3. And since the bases match, I can go ahead and add the powers as long as I get a common denominator because they're fractions. So I can multiply this one by 3 over 3. I can multiply that one by 4 over 4. And then that gets me to 2 to the power of 9/12 times 2 to the power of 20/12. And then I can just go ahead and add that up. So that would end up being 2 to the power of 29/12. 2 to the power of 29/12. And then actually I can simplify that. Into some whole numbers and then rational numbers. So because 12 goes into 29 twice, right? So that's like 2 squared. And then I would have 5 left over. Because 24 divided by 12 would be 2. That would leave me with 5 over 12 left over. So 2 to the power of 29 over 12 is the same thing as 2 squared times 2 to the power of 5 over 12. And so then that would be 4 times 2 to the power of 5 over 12, which is 4 times the 12th root of 2 to the 5th power. So this answer is sufficient if you're only asked to convert into rational exponents. If you're asked to simplify the radical expression, then you'd have to go this extra step, figure out how many 2's you could take out of there, and then how many 2's would be left inside. So I guess this would be altogether, it's 4 times the 12th root of 32. That's our final answer for simplifying this radical expression all the way as far as it can get. Okay, so now let's look at number 12. So similarly before, we were not able to add these because of the fact that the indexes did not match, right? So the index and the radicand have to match in order to be able to add them, and none of them do right now. But I can reduce this index by using rational exponents for the 4th root of 400. So that's what I'm going to do first. So 400, I can think of that as, it's 20 times 20, right? 20 times 20, because 2 times 2 is 4, and then you just have these 2 zeros, right? 400. Okay. So this is 3 times the 4th root of 20 squared. Okay. 3 times the 4th root of 20 squared. And then plus 7 times the square root, and then 125 is 5 to the power of 3, right? 125 breaks into 25 and 5, and then 25 breaks into 5 and 5. So this is 5 to the 3rd power. Now I'm going to reduce this square root. I'm going to reduce this down to a square root by converting it to a rational exponent. So I get 3 times 20 to the 2 over 4 plus 7 to, well, okay, this one, let me think of it this way. It's the square root of 5 times 5 times 5, right? So I can go ahead and take out a square root of 5, according to our simplifying, right? And then just leave that one single factor of 5 under the radical. So I simplify that radical. Meanwhile, over here, I'm just trying to get this fourth root to be a square root, and I see that I've got a perfect square in there, right? 20 squared. So fourth root of 20 squared is the same thing as 20 to the power of 2 over the index of 4, and then that can reduce to 1/2. So now I have 3 times 20 to the power of 1/2 plus 35 times the square root of 5. So that's 3 times the square root of 20 plus 35 times the square root of 5. Okay, now that I got down to the square root, I can simplify the square root of 20. Now 20, we know, breaks into 4 and 5, and then 4 breaks into 2 and 2. So let me take this over here. So I can say that the square root of 20 is really the square root of 2 times 5, right? 4 times 5. So I can take out the perfect square of 2. And then, of course, I still have the 35 times the square root of 5. So then I'll take that out and multiply that to the 3. This single factor of 5 has to stay in the radical. And now look at that. I've got matching indexes, right? The index is now both a 2, because now they're both square roots. So I have matching indexes. I can check that off. And matching radicands. Both have square roots, both have radicands of 5. Now I can go ahead and combine them together. Of course, this is 6, right? 3 times 2 is 6. So I can add 6 plus 35 and get 41 times the square root of 5. So now I was able to add these expressions together because I could reduce that index. Because there was a perfect square inside. I could reduce the index down to a square root and then reduce the square root to get the matching radicand, and then went ahead and added the outside numbers together. Now for the last question type, it's just kind of overall simplifying using a combination of rules of exponents and then also rational exponents. So the first rule of exponent that I'm going to use here is the one that says that if you have two different bases raised to the same power and they're being multiplied together, you can just distribute that power. So this is the same thing as x to the 2/3 times negative 12 times y to the 1/6 times negative 12. And then when you multiply fractions, you just multiply straight across. So then, or you can cross cancel. So in this case, the 3 reduces with the negative 12 to leave a negative 4. 6 also reduces with the negative 12 to leave negative 2. And then I can multiply the 2 and the negative 4 here together for the x. So I get x to the negative 8 times y to the negative 2. So that's what the first thing was, just to multiply 2/3 by negative 12 and negative 1/6 by negative 12. Oh, by the way, yes, that's the other thing. When you raise one power to another higher power, those powers multiply. That's what I meant to say. That's why I multiplied 2/3 with negative 12 and 1/6 with negative 12. But now that I have these remaining negative exponents, I have to remember what that means, which is to take the reciprocal of both of those. So they both end up in the denominator. And then when you take the reciprocal, you make those powers positive. So the final answer for number 13 ends up being 1 over x to the positive 8 times y to the positive 2. Now in 14, I would start similarly. I would start by just distributing the 1/2 power to literally everything in that fraction. Okay, so I get 81 to the 1/2 times y to the 16 times 1/2 divided by 16 to the 1/2 times x to the 12 times the power of 1/2, and then reduce all of that. So remember, 81 to the 1/2 is the square root of 81, right? It's the square root of 81, and then 16 times 1/2 is 8, right? Because that's like 16 over 1, and then I can divide 2 into 16 and get 8. And then 12 times 1/2 would end up being 6, because 2 goes into 12 6 times. So I have the square root of 81 times y to the 8th power over the square root of 16 times x to the 6th. And then, of course, we know the square root of 81 is 9. And the square root of 16 is 4. So we can evaluate those, right? 81 to the 1/2, we actually could find the value of. 9 is the one out of the two factors that multiply 81. 4 is one of the two factors that multiplies to 16. These are the square roots. So this is our final answer here. Now, in our last example, number 15, we just basically have a multiplication problem with numbers, 5, 2, and 3, and then bases with different powers. So the way we handle that is we can go ahead and multiply the numbers together. So 5 times 2 is 10, times 3 is 30, right? That was the product of 5 times 2 times 3. Now for the ends, we would add all of those exponents together, right? The positive with the negative, we would add it all up because these ends were connected through multiplication. So it might help to get common denominators. Well, actually, maybe I'll start with the whole numbers first. The 3 and the negative 4. So this is 30 times n to the negative 1 plus 1/2, because 3 plus negative 4 is negative 1, and then I still have to add the 1/2. So negative 1 plus 1/2 would be negative 1/2. So this ends up being 30 times n to the power of negative 1/2, which is the same thing as 30 divided by n to the power of 1/2. 30 stays in the numerator because the power for 30 is a positive 1. The only thing that actually moves down to the denominator is n to the negative 1/2, because the n, and only the n, has a negative exponent. So that particular one goes down into the denominator. But we have to consider what that actually means. What that means is that I'm now dividing by a square root, right? Because a 1 over 2 power means an index of 2, a second root, a square root. So if we need to rationalize the denominator, like we had learned to do before, if we're having to write this in radical form, I would then have to multiply the numerator and the denominator by rad n to get something that looks like this. 30 times the square root of n divided by n. That would be in simplest radical form. So you could either leave the answer like this, 30 times n to the negative 1/2. This is in rational exponent form. Or 30 times the square root of n over n. That is in simplest radical form. And they're both equivalent to this, by the way. 30 times n to the negative 1/2 is equivalent to 30 divided by n to the 1/2. And that is equivalent to 30 over the square root of n. These four things are all equivalent expressions. And then when you're being asked to put it in simplest radical form, this would be the one to go to. If you're being asked to put it in rational exponent form, it would either be this or that, depending on whether they say to leave your exponents positive or not. So that concludes our lessons on skills 10 and 11, which is simplifying and converting between rational exponents and radicals. So you will be working on some practice related to that now. And if you need any help with that, let me know. Bye.